Come on. Okay, so the lecture capture camera isn't, oh, there we go, finally. Okay. So, my plan for most of today is to go over any parts of the test that a lot of people have questions about, and maybe get a little bit into chapter 20 if we have time at the end. It's a pretty short chapter, so it shouldn't take us too long even with the missing day. Okay, so first of all, the average was 72.4, which is awesome. So there's a 2.5 curve added to whatever the number on the front of your exam is. And the grades are posted in Canvas already. So after today, after my 11 o'clock lecture, I'm going to parcel the exams back out to the TAs. So if you want it back on like Monday, you can just go get it from your TA in recitation or by contacting them ahead of time. Also, as a reminder, the Sapling Chapter 19 is due Wednesday at 9 a.m. and the exam regrades are due next Friday at noon. So any questions about those things before we start getting into the exam? Okay, cool. So I guess, so we got 7 problems on here, not 8 like I erroneously typed on the front cover, where it says 8, that's actually a grade for number 7. I guess, let me just run down the numbers and see, like, raise your hand for all the problems you'd like me to go over. So problem number 1. Okay, no one wants me to go over that one? All right. Number 2. Number 3. All right. Number 4. Okay. Number 5. Number 6. Okay. Number 7. Yeah. Okay. Okay, cool. I think like I saw just an increasing number of hands go up for each one, except for 6. So maybe let's start with 7 and work back. Okay. Oh, and the key's posted online now, by the way, too. Okay. So number 7 here, I think the easiest way to handle problems that are like this are pretty much just like scan ahead through the problem and see where it actually gives you the name or structure of any kind of compound that you can get out of this, because until you get that, it's going to be pretty tough. This one tells you that phthalic acid is pretty much the only compound given. So whatever A is, if you oxidize it with KMNO4, you're going to get phthalic acid here. Okay, so we know that A is something with an aromatic ring. It also has 9 carbons. And if you do the math, it has 5 degrees of unsaturation. You don't have to do that, but it sure makes it a little bit easier to work with. So basically it's going to look like phthalic acid with one extra carbon, with no oxygens, and with one extra degree of unsaturation somewhere, like either an alkene or a ring potentially. Okay, so we also know that if we take this, react it with NBS, it gives a single monobromo compound B. Okay. Actually, I guess just from the first bit of information here about phthalic acid, we can pretty much narrow it down to one of two structures. So we know it's got to have either so one extra carbon on here, and with all the oxygens removed, gives us either this or this with a ring there. So let's figure out if we can rule it down or narrow it down to one of those. Okay, so NBS on this thing gives us a single monobromo compound. If we take either one of those, you get a bromine on there, or okay, so even though this is technically a benzylic carbon, we know that we can't make radicals very easily on a vinyl carbon. That's kind of the first part of chapter 18 was all about that. So we're just going to get a single monobromo out of that. When B is dissolved in aqueous acetone, it reacts to give two non-isomeric compounds, C and D. Okay, so catalytic hydrogenation of D gives back A. Okay, so we take whichever one of these we happen to have, react it with water and acetone, and we get, so if we're doing it to here, we got a secondary alkyl halide, weak base, poor nucleophile, probably going to be like an SN1E1 mix. So either this alkene plus this alcohol, or if it turns out that we actually have the second one, we're going to get okay, so here's where we're running into problems for this one. Can we do E1 on this molecule? Right, because we can't make a double bond here. So that is not going to happen. Or can we do SN1? Yeah, that's going to work okay. So that's pretty much the only product we're going to get out of this. So that kind of helps rule it down to it's got to be the ring option. If you didn't catch that, you could still figure it out from seeing that catalytic hydrogenation of D gives you back A. We don't know which one of these is C and D, but if we hydrogenate one of them, then that gets you back A for the ring version of A. So it's got to be D and C. We also know that that rules out this one because if we hydrogenated this one, we're not going to get our alkene back safely. So no on that, no on that, and no on that. Okay, and then when optically active C is oxidized, all right, so here's C getting oxidized with CrO3 and pyridine. Then we're going to get a ketone out of it. So like that, which is E. Okay, so this should be A, B, C, D, and E. Okay, so I saw a lot of people that got the top structure with the alkene, which works for the first couple steps, but then once you start doing like eliminations or hydrogenations to it, things start going wonky. Okay, so questions about that? Yeah.
Do you assume that NBS is 1 mole? Because if it was in excess, it would have 2 benzoic positions that you could add.
So the fact that they tell you a monobromo compound implies that the stoichiometry must have been such that it only adds once, yeah. But yeah, if they hadn't told you that, then yeah, it might add any number of times depending on how many benzoic carbons there are. I guess one thing I didn't specifically address when we covered it is NBS usually maxes out at 1 bromine per benzoic carbon, just because having 1 on there makes it a little less stable to make the radical there on subsequent passes. But yeah, you're totally right. You could still like stick a second bromine up here if there were enough around. So, good question. Okay, yeah.
So on that note, one of the reasons why I did stick, on my spread, I stuck to the first compound with the alkene is because it said the monobromo. So I assume that it would add, the BR would add to both allylic positions for benzoic positions. But yeah, I think that was just one of the things in the construction that that have to roll it out.
Huh. I guess it's sort of like, you remember when we did radical halogenation from back in OChem 1, where we're like I don't know, so you get something like this, and we're like Br2 and H nu, and then we're like show the monobromo compounds only, because you could do the stoichiometry such that you could add to both carbons, but we're just interested in adding 1. I guess that's kind of the same thing here, where we're like, okay, if we're getting just the monobromo compounds out of this, then it's just going to be that 1 product. I guess that's kind of the parallel that I was kind of thinking of. So yeah, does that kind of, yeah. I guess like it is a little sketchy on the wording. I can sort of see that, but I might have to think about that one some more, but yeah. And when I say I mean the Loudon textbook problem that I totally copy-pasted this from. Yeah. Yeah. Okay. Yeah. Okay. Uh-huh.
For molecule C,
Mm-hmm.
could you also do an SN1 with acetone?
Temporarily, yes. So I guess what you'd have briefly is like this kind of a deal going on, but the problem is you got a positive charge on there and there's not a whole lot else you could do. I guess you could attack with water at that point, but I don't know, acetone is not a great nucleophile in the first place, so even if it got that far much of the time, it probably would just drop right back off as soon as water came in and like kicked it back out. So. Okay. Other questions about that one? Yeah. Sorry? Why would the bromine not attack here? So it might. So then I guess you're getting into like what sort of looks almost like a hemiacetal formation at that point, which if you still have a bunch of water around, we know the equilibrium is likely to drive back to the reactant side. So yeah, I mean, you totally could make like some structure of stuff added to the carbonyl like for a little while, but we know now that with water around, it's kind of doomed to not last very long. So. Okay. Other questions about that? Okay, cool. So I didn't see many hands for 6. Does anyone want to go over that one? No? Okay, cool. Okay. So this one, I found a cool paper that sort of uses several of the reactions from the last couple chapters and puts them together to make this cool fused ring structure. So that's pretty much what's going on here. Okay, so the first step is you have 6. You've got boron and your iodine. I'm not even going to bother drawing all the ether groups hanging off both rings, but they stay unchanged through the whole thing, so not really that interesting. Okay, so these two groups together should make you think Suzuki, especially since the other reagents written on the arrow are the catalyst and the base that we need to do Suzuki. Okay, so you make that new aryl-aryl bond. Okay, so that gets you to here. We have a couple carbonyls hanging off, which we can't do anything very interesting with them together right now, but what we can do is replace them with a couple CH2s, which we do by a Wittig reaction. I sort of drew this in an orientation you might not be used to seeing just to fit it into the arrow between the boxes, but this is pretty much just a Wittig reagent with a CH2, so I saw a few people that actually redrew it as this thing, which might make it look more familiar. But this is just going to replace both of your double bond to carbonyl with a double bond to a CH2 group. Remember that anything written on the arrow is in excess unless we specify otherwise, so we got enough to do both of them. Okay, so that gets us to here, and now we're ideally set up to use grubs and close that loop down. Which gets us to here. And then some magic happens over the course of 6 steps, and they get rid of aromaticity and add a whole bunch of extra things, including another bridging group, and get hasubanonine out of it, but that part we haven't covered. Okay, so I just thought this was a really cool sequence that sort of puts several things together in a way that gives us a new fused structure that we haven't seen before. So, questions about that? Okay, cool. So moving backwards, number 5. Does anyone want to go over that one? I don't think I saw too many hands on that. Yeah, that one's pretty self-explanatory, I guess, if you go through that part of the notes. How about 4? 4? Okay. Okay, so for A, oh, that's not that. Okay, there we go. So this one is diphenylamine and H+. Okay, so I guess just from looking at the reagents involved, we've got a carbonyl, so that tells you we're doing chapter 19 something or other. We have an amine here with 2 R groups on it. So even if you don't really remember how things are going to end, you might remember what type of functional group is going to result from this setup. Does anyone remember what we're going to make here? Yep. Yeah, so even if you look at this and you're like, I have no idea how to start this, if you remember secondary amine and a carbonyl gives you an enamine, that's kind of where we're heading with this. Okay, so we're going to start out in acidic conditions, protonating the carbonyl. Like that. And then now it's primed for attack, so the nitrogen can come in, get involved, kick that up. Okay, so that gets us to here. The next step you can either show as two separate steps or as one step, because we got to get rid of this H and add an H over here. In the key I just showed it a one-step deal. Okay, so this is all pretty much like hemiacetal formation so far. And this part is like we're progressing on towards acetal formation, only it's an N instead of an O. Which gets us to here. This is where things get a little bit different from acetal formation, because we can't do anything to quench the positive charge on this nitrogen. So we gotta go a little bit further away to sort it out. Pull an H off of here, and you can kick the bonds over, do like an E2 sort of looking thing. And get an enamine that way. Okay, so questions about that one? Okay, cool. All right, so the second one. All right, so flipping through the exams, like I think a few people are still a little bit shaky on the difference between SNAR and EAS and what kind of charge you have on the ring for each of those. So this one, actually I'm going to keep the double bonds the same as they are in the key just to keep it easier. Okay, so this one, you have a ring with a nitro group on it and a fluorine leaving group. That should make you start thinking about SNAR right off the bat. But the bigger tip-off is the other reagent that we have is a nucleophile. So we're going to be trying for nucleophilic aromatic substitution. If we had an electrophile around, something with a positive charge or a big delta positive, that would be an electrophile, so we'd be doing electrophilic aromatic substitution. Okay, so we take our nucleophile, we come in, we attack the ring, right where the leaving group is going to get spat out, because that's pretty much the only way to actually end this reaction in a meaningful way. So we attack here, this double bond's got to break, and we get into this deal, and now we're looking at actual resonance forms. Okay, so we can show it here, or we can show it here, and reminder that the arrow pushing for this, even though like the charge is still hitting the same 3 spots around the ring on alternating carbons, plus potentially getting pushed out to a side group, even though that's happening the same as it would during EAS, our arrow pushing looks different because here we've got a minus charge, so the arrows start here. When we were doing EAS, it was a positive charge, and so the arrows had to end there, and so the arrow pushing looked a little bit different. Okay, so this is one option for resonance. And now I'm actually going to draw out the nitro group. You could draw it out in previous ones if you wanted to, but it wasn't necessary. Okay, so this is where the nitro group is actually going to do its thing. The whole reason why this works so well is if we take this negative charge and kick it out towards the nitrogen, then we can break that bond up onto the oxygen. So even though there's some multiple different types of atoms involved, if you look at this, this is actually the same as the 3-atom unit pattern that we've been using for resonance the whole time. So here we've got a 3-atom group that has 2 atoms double bonded, one with a charge, and we swap which end is which. Here we also have a 3-atom unit. 2 atoms have a double bond, one has a charge, and we swap which end is which. Just because one happens to be O and one happens to be N doesn't change our arrow pushing, as it turns out. We're not actually involving any like lone pairs getting involved off of any atoms. Well, I guess the carbon, it's lone pair, but that's the same as over here. But everything else is pretty much exactly the same as our regular old arrow pushing around the ring. But what it does for us is gets us to an extra stable version of the same thing, because now we don't have to deal with a carbanion at all. Minus charge has gotten shuffled aside onto an oxygen where it's way happier and more stable. So this is why nitro is good at stabilizing this reaction, because you can sort of take some of the charge burden off of carbon and stop having a carbanion a lot of the time. Okay, and then one last form. And by the way, you could have drawn these forms in any order. I'm just sort of doing it the shortest route between them. The last option is we do that 3-atom pattern and get the charge over here. You could show that as like branching possibilities off of here, although then the arrow pushing might be a little bit confusing. Or if you gotten to this point already, you could just do what you need to get, I guess I'll come off of here just to keep things consistent. All right, so we are, if we reverse back to here, it would show an arrow going onto this carbon. If we want to show it going over here, we can just sort of hop over that carbon and get it onto there. Okay. So that's all 4 resonance forms that you needed to show. And then the last step, which you can show happening to any of the 4, it's probably easiest to show coming off of the one that you drew last, because this doesn't have any arrows coming off of it. But at some point, you just need to boot out the leaving group, and that's not right at all. There we go. Oof. Okay. So have the minus charge kick down, reform the double bond, and boot out the leaving group. Okay. So questions about that one? Okay, cool. All right, so we might not have time to do the entire synthesis one. Do you guys have a preference between A, B, and C? Let's see a show of hands for A. Okay, B? C? Okay, I think I saw more for B than for C, so let's do B. Okay, and for all of these, there's probably like at least 5 or 6 different valid routes to get each of these now. I just put on the key the one that popped into my head first, but you know, if you had steps that worked, that didn't cause any problems with any other functional groups along the way, then you got full points. Okay, so B. So I had a lot of people ask during the exam, actually. Probably like a dozen people asked, like, can I just start with this, do Friedel Crafts to it, and get the target molecule? What's wrong with that? Nope. So it would work. Like, you could totally do Friedel Crafts to this molecule, but how are we going to control regiochemistry coming out of this? Like, the D could be anywhere relative to the acyl group. So one of any 3 different possible products. Okay, so we're going to have to figure out something a little bit cleverer. If we start out with, say, a bromine on there, yeah, I think if you did do this method, you still got some points, but you know, it's not the best way to do it because you're going to lose probably about, actually, I guess like not only could you stick the acyl group on anywhere here, you could also like accidentally replace the deuterium. So I guess there's 4 different possible products, one of which just doesn't have the deuterium in it at all still. So even though, you know, we use ortho para directors sometimes and we're like, yep, you're going to have to throw about half of it away because it's ortho when you wanted para or vice versa. That's still like the best way to do it, unfortunately. But here you got better options. You can do better. Okay, so let's instead start with a bromine in that location because at least bromo is ortho-para directing and won't actually get replaced itself potentially during this reaction. A few people started with straight benzene, which is fine, but you can also start with bromobenzene because we're not breaking the 6-carbon limit on this. Okay, so now if we acylate, you get to bromine. Okay, so what steps am I going to use if I want to replace this with a deuterium? So SN1, SN2 isn't going to work, which I saw a couple of people try. But we know deuterium is basically a fancy hydrogen. So in the past, when we wanted to replace bromine with hydrogen, we turn it into a Grignard or organolithium and then quench it with water if we want a hydrogen. If we want deuterium, we can use D2O. So at a first pass, we're just going to think about doing it this way. So make the Grignard, and then D2O will fix that up. Okay, what's wrong with this though? Yep, yeah, carbonyl is going to get messed up as soon as we get to this point. So this is now looking like a classic protect, do some Grignard stuff, then deprotect at the end. So I don't know if I got time to draw the whole thing out, but protect first, and then deprotect should be sort of your plan for figuring this one out. Okay, so I guess this one, like there's some order of operations flexibility depending on whether you brominate or you know, exactly when you protect, and which organometallic, but this one you're fairly limited if you want to get it to work reasonably well in decent yields. Okay, questions about that one? Okay, cool. So I think I'm just going to wrap it up there for the day. The key's posted online if you want to compare your answers, but as a reminder, the regrade stuff is due a week from now, so staple a piece of paper on the front if you want it looked at.
I just had a quick question. So, why doesn't this work out? Like, are you not allowed to do perform like SNAR with like